I like to start my semester off with a yang. Fire. It has been a tool at humanity's side since the Paleolithic era. Early humans used flames for warmth, to cook food, to light up their path, and even to fight and ward off animals. Scholars believe that Homo erectus learned to control fire approximately 1 million years ago, with some theories pushing the number up to 1.7 million years ago, and more conservative numbers estimating only 200,000 years ago. The technical definition of combustion is a rapid oxidation of material that releases extreme heat and light. Essentially, a combustion produces fire. All parts of this definition are important. For example, rusting is an oxidation of iron, but because it is neither rapid nor produces intense heat or light, it cannot be considered a combustion. The burning of propane, however, fits all the criteria. That does raise the question, what is flammable? There is only one real way to find out. But there are some guidelines for predicting flammability. Flammable materials have to be high energy to fuel the flame. Organic molecules make up a large portion of the list. Alkyl molecules like ethanol, benzene, and propane are all flammable. Reactive metals such as magnesium, sodium, and rubidium react violently when exposed to an open flame. Lower energy materials tend to not make good fuels, as they don't have the energy to support a flame. Fully oxidized compounds such as water and carbon dioxide cannot be oxidized further, making them categorically inflammable. The basic reaction for a combustion involves some fuel combining with oxygen to yield carbon dioxide and water. The reaction can be written with a delta above the reaction arrow to signify the need for extreme heat to start a reaction. When all carbon is converted to carbon dioxide and all hydrogen to water, it is called a complete combustion or a clean burn. There are exceptions, of course. More complex fuels don't always combust completely and produce side products. Benzoapyrene is one such product found in engine smoke and is a dangerous carcinogen. Atoms other than carbon and hydrogen, i.e. heteroatoms, have their own behavior in combustion. Within the confines of a general chemistry course, these will usually be given as needed. Before any meaningful calculations can be made, any combustion equation will have to be balanced. These are balanced like any other chemical equation, making sure that the atoms that make up the reagents are equal to the atoms that constitute the product. It's usually easiest to balance carbon and hydrogen first, and worry about fractions and oxygen afterwards. There is no shame in taking more than one step after all. Combustion data assumes a clean burn, and comes as masses of water and carbon dioxide. From the masses, determine the number of moles of each compound. The molar ratios are telltale of the relative number of constitutive elements, i.e. the empirical formula. The empirical formula is not necessarily the same as the molecular formula. The empirical formula is the lowest common atom ratio. Sometimes this means that the true molecular formula is a higher multiple of the empirical formula. Without more data, it is difficult to reliably determine the molecular formula from an empirical formula. There may be tricks, but these are usually fraught with guesswork and conditions. Combustion analysis alone often can only determine the empirical formula and stop short of the molecular formula. This is a minor limitation for such a simple and useful tool. This oxidative reaction has provided heat and light for our ancestors since prehistory and is useful still as a spectroscopic tool. The fact that it produces consistent products in carbon dioxide and water makes determining empirical formulas conceptually simple. It is difficult to control, but faithful, and oh so beautiful. A pyromaniac's desire. Thank you very much for watching, and join us next time to find out how a cannibalistic snake was responsible for the understanding of an entire class of molecules.